So thanks to the organizers for inviting me here. Sam's not here, but everybody else. It's been a wonderful program. Great place to be working and doing research. Today I'd like to talk with you about absolute robustness, what it means, and specifically what it does in deterministic and stochastic systems. I'm going to tell you a little bit about the biology behind it. Then I'm going to tell you about the deterministic framework, what it is, and then we'll move on to the stochastic aspects of it, and I'll give you some examples. Anytime, please stop me, and we'll keep this as informal as possible. First, a little bit of biology. These are so-called two-component systems. They're very common in bacterial biology. Two-component systems are called two-component because they have two proteins that work together in a pair. The first protein is a sensory protein. In this case, it's called MZ. MZ, sensory protein that senses osmolarity in E. coli. And it signals to the second protein, which is called OMPAR, which is the actuator. So the OMPAR is a transcription factor, and it does things about it to change the osmolarity of the cell. So MC senses, OMPAR acts.
What is osmolarity?
Osmolarity is something that we don't particularly deal with macroscopically, but that can kill a cell. For example, too much sugar or too much, basically it has to do with the osmosis not blowing up the cell. If the osmolarity is not right, you can have too much water coming into the cell and blowing it up. Because, E. coli has the membrane does not have, the tension does not resist so much pressure. But you're asking the wrong person, actually. I'm not.
It's the difference in concentration of stuff between the inside and the outside of the cell.
Well, there you go. Okay, so MZ is a kinase. It attaches a phosphate a group to OMPAR and thereby activates it. But the interesting thing is MC also dephosphorylates OMPAR through a totally different mechanism. It's almost like it has a different domain with the phosphatase, and it takes away the phosphorylation. So you would think if you have 5 times more MZ, let's say, then you're going to phosphorylate OMPAR 5 times faster, but you also dephosphorylate it 5 times faster. So it shouldn't matter too much for the final phosphorylated concentration of OMPAR. You would think without doing any math, that would be like a natural thing to think. So Eric Batchelor and Mark Julian went ahead and they did this experiment where they changed dramatically the concentration of MZ in the system by 2 orders of magnitude, and they looked at the active OMPAR concentration. And you can see that even though this is 100-fold, the changes in the concentration of OMPAR phosphorylated is not that big. It's basically about 2-fold, 3-fold, 4-fold, something like that. But the total amounts of MC are 100-fold. This is what they described as a strong form of robustness. Not quite absolute robustness yet, but just a strong form of robustness. These guys over here, it's not entirely clear how to interpret it. This ratio here comes because of the fact that you cannot directly, or at least back in 2003, you could not directly measure the amount of phosphorylated OMPAR. So what they did is they looked at the downstream proteins that were active on it, and they took ratios, and the larger the ratio, the higher the putative concentration of OMPAR. And then there's a normalization, I believe this is just normalization, so the fold rate would be the same even if you didn't normalize. Okay, now something that is perhaps more surprising is if you take the total OMPAR concentration and you change it also about 100-fold or so, then once again, the active downstream effector, OMPAR phosphorylated, also doesn't change very much, even if you change this 100-fold. Okay, so first of all, why is this important? Well, think about it. If you look at a tissue, cell tissue, the total protein concentrations from cell to cell can change dramatically. You can have 5 times more of a protein in this cell than in the next one, having to do with, for example, noise in gene expression. Sometimes the relevant molecules that express the genes are not in very high quantities, and stochastic effects create large variabilities. So you would like to somehow cope or address this large variability in such a way that the output does not change very much. So this is evidence of a form of output stability in the face of total protein concentration changes. And what the mathematics of this absolute robustness is about is to try and find out mechanisms to explain this behavior.
Sorry, so I understand why it's surprising that the phosphorylated AMP-R is robust to total AMP-R, but why is it surprising that the concentration of MZ doesn't affect phosphorylated AMP-R unless you know MZ is somehow regulating the expression of AMP-R?
Well, it's regulating, but you would think if you have, let's say, let me just say for the moment, if MC did not have a phosphatase domain, but only a kinase, then you would expect the more MC you have, the more on-par you would have, the more phosphorylated on-par you
You're
would
saying
have.
competes for the phosphate.
No, it phosphorylates it. It
Okay,
phosphorylates
okay.
on-par, right? So the more kinase you have, the more it phosphorylates it, right? So it's a regulator, but it doesn't really matter how much you have of it. It's kind of a surprising thing in that sense.
So is the phosphorylation related to the signaling?
Yeah, of course. The moment that this changes in osmolarity, it changes the phosphorylation of on-par. Okay, so this slide you probably already know, but I need to mention a part of it later, so I'm just going to mention it.
Sorry.
Yes, Peter.
So how does that even work? I mean, if the thing's robust to, oh, I see, you're saying it's robust to MZ concentration, but if the osmolarity changes, then of course the value of AMP-R phosphorylated will change.
Right.
Okay.
That's the. Okay, so just again very quickly, you have a set of reactions, chemical reactions. I'm going to use the mass action formalism for the whole talk. I believe some of these things you can generalize to non-mass action necessarily, but for the sake of simplicity, I'm sticking to mass action. You can in a very deterministic way, you can create an ODE for these reactions, and then you can also write down the stoichiometric matrix for the system, which basically tells you for each reaction the net number of molecules that are produced and destroyed in the reaction. I'm going to use this in a moment, so I wanted to mention it. It's a toy model. Toy model basically meaning the simplest possible system that has this absolute robustness property that we're going to study. A plus B goes to 2B, B goes to A, with reactions rates K1 and K2. When you write the ODE, it looks like this. You set it equal to 0, and you get K1AB equals to K2B. You set this equal to 0. And then assuming that B is different from 0, you can cancel B on both sides. You get A is equal to K2 over K1. Now, why is it surprising? There's actually a mass conservation going on here. The total amount of protein, A plus B, is constant. You can think about A and B as being active and inactive versions of the same protein. The protein is not produced or destroyed, only the activity is changing. So if you start, for example, in this diagonal, you stay in this diagonal because A plus B is constant. However, the steady state of each of these stoichiometric classes is the same for A. You see, A is always equal to K2 over K1. If you think about A as being the active version of the protein and B as the inactive version, then this is a very strong form of robustness because you see the steady state, the active version of the system is the same no matter how much you have of the total amount of the protein. Except, there's an exception to this. If you have too little, if A tot adds up to less than K2 over K1, then of course you cannot have A equals K2 over K1, and then something else happens. Actually, basically, A is something less and B is equal to 0. But if you have enough of the total amount of protein, then the concentration of A is always equal to K2 over K1. Okay, so that's the definition of absolute robustness. It's a protein with the property that regardless of the total amounts of the proteins in the system, all the proteins in the system, at steady state, it has the same concentration. All right. Now, if this was the only example, it would not be very interesting. As much as I like this toy model, I wouldn't really care because it's only one example. But it turns out there's a large family of systems that have the same property. Now, you guys might have heard about deficiency theory before. This is very much in the framework of deficiency theory. Just very quickly, when you have a reaction network, you look at this as a graph. Just look at these as nodes, and these as edges between nodes. And here you count the number of nodes. In this case, it's actually 4 plus 3 plus 3 is 10. This is the number of connected components. In this case, it's 3, 1, 2, 3. And this is the rank of the stoichiometric matrix, which I mentioned 2 slides before. And you do this sum here, and that's what you get is the deficiency. Notice that the deficiency you can tell without knowledge of the parameter values. K1, K2, K3, you don't know, you don't care. The deficiency is the same. Also, what else? Yeah, okay, so the deficiency is only a function of the topology of the system, if you will, not of the parameters. Okay, so now, I need to tell you one more thing, which is this idea of non-terminal node. Non-terminal nodes are nodes with the following properties. Suppose that you start, for example, right here in this node, and you start walking following the direction of the arrows. So you start walking, you walk from here to here. At some point, you walk over here, and you cannot come back. Okay? So this is called a non-terminal node because if you start walking, eventually you cannot come back. If it's not a non-terminal node, it's called a terminal node. So these are the terminal nodes. These are the non-terminal nodes. So you can see very quickly again what non-terminal nodes are. Okay, so now the theorem says, suppose that lambda is 1, delta is 1, the efficiency, and the system has a positive equilibrium, and that there exist two non-terminal nodes, two of these, blue ones, that differ by a single variable a. Then a is absolutely robust. Okay, so in this case, you see anything that is that differs by one variable. Well, actually, it's right here. Xd and xd plus yp. These two complexes differ by the variable yp. So by this theorem, yp is absolutely robust. And you can tell this just from looking at the network without doing any calculations, without knowing parameter values, and so forth. Incidentally, this network is none other than a model of the system of MC and on par. Basically, MC is X, on par is Y. This is just MC changing its form, being phosphorylated, dephosphorylated. This is MC phosphorylating on par, and this is another form of MC dephosphorylating on par. So here you can see the bifunctionality of MC. And in fact, it's actually very important, and you can think about it as, in a sense, decreasing the rank of the system because these reactions are very similar, involving very similar molecules. You can think about this as a reason why the system has the efficiency 1 to begin with. In fact, even though it doesn't have to be like this, every single example I've seen is biologically relevant, like using actual molecules, has a bifunctional enzyme. So bifunctional enzymes are very important for absolute robustness. And they do show up quite a bit. In fact, all these I should say all, but most of these two component systems have these bifunctional properties. So it could be a very widespread mechanism. All right, what else? I think I already said all of these things. This theorem was proved in 2010 by Geishinar and Mari Feinberg. It's become basically a seminal work in this area. And from now on, I guess we're going to start talking about the stochastic version of this. Right?
Excuse me.
Yes.
Yeah, sorry, try. Can you remind us what is robust? What is absolutely robust?
Yes.
What is the definitions?
Yes. So the definition of robustness is, I guess, you can see it in this example. Robustness means that this variable a at steady state has the same concentration regardless of the total amount of the protein. So regardless of how much there is of the proteins overall, the concentration of A is always the same.
Sorry.
Yeah.
So this is the definition for this system. So this is something that is more than for two systems. This is the general definition. So this is what is meant by robust.
Absolutely robust.
Absolutely. And what is the difference with robust?
Well, robust has many different meanings. I mean, you ask 10 people, you get 12 different definitions of robustness. This is a very specific form of robustness.
So it's invariant against just dilating all species by the same number or arbitrary changes to the other species?
The total protein concentrations you can change arbitrarily. As long as there's a small fine print that there needs to be enough, so that this protein has enough to have that concentration. But as long as you have enough, no matter what the total amounts of all the other proteins in the system are.
So when you say total amounts, it's invariant with respect to a one parameter family of concentrations?
Not necessarily. If you prefer, another way to define this is, it doesn't matter what stoichiometric class you're in, regardless of the stoichiometric class, you always have that one protein.
I don't know what this means, stoichiometric class.
Okay, fine. So, well, okay, let me give you another example. For example,
reachable from a given initial condition.
Okay.
right. So for example, in this system, you have a total amount of X of the MC and a total amount of Y of the on par. And regardless of the total amount of on par and of MC, whether they are phosphorylated or not, the concentration of this molecule Yp is always the same.
But in order to be able to talk about something like that, does that mean that your system needs to have a conservation law?
Yes, very good point. You need conservation laws in order for the absolute robustness to be relevant at all. If, for example, in this system you don't have protein production and degradation, because that would destroy the conservation of mass, and there's nothing to be robust to.
Okay, so, but I think following on from Pete's question, so is there a unique conservation law, or the like, I mean, for example, in this system,
The
What-
system has two conservation equations, conservation of x, MC, and conservation of 1
okay.
Yeah.
But then in that context, what is to you, what it is robust with respect to what? Changing
to the total amount of.
any of the two.
Of any of the two, yes. Yes.
So the definition would be that you have, I don't know, n conservation laws. It doesn't matter what the value of these conservation laws are.
Yep.
There is at least one variable that doesn't change steady state.
Yes,
Okay.
correct.
Can I just interject? I mean, another way to say this, I think, getting rid of like the word proteins or anything, just you have a system of differential equations, you look at the set of equilibria, of positive equilibria, this one species at all of the equilibria is always the same value.
There you go.
I don't know if that's helpful.
Is each conservation law equivalent to one robustness and vice versa? Are they equivalent things essentially or not?
In this case, we assume that the variable is robust with respect to all conservation laws. So there's one robustness, one robust variable, but there's many conservation laws.
There's no such thing as a negative.
Correct.
You could have 0. I'm saying like,
Sure.
okay,
Can I ask
I say positive equilibria, you can throw
one last thing? So you said that the nodes, I didn't really get what you meant about nodes, because I would think that the node X is one node, XD is one node,
Yes.
XP is one node.
Yep.
Okay, it's just because you have XP plus Y together, you call it non-terminal node, so I'm a bit confused.
Yeah, so the definition of the terminal node, everything that's blue here, and the definition is basically based on the structure of the graph. Forget about this being a chemical reaction for the moment, just being a graph. If you can walk around and not come back, then this is a non-terminal node.
Okay, but but in my mind, what a node is Y, XP. But now you're saying that XP plus Y is a node.
Yeah, the nodes are not species
Okay.
necessarily. The nodes of this graph could be combinations of species called complexes. For example,
Okay. Fair enough.
XP plus
Fair
Y
enough.
is a node
Okay.
of the graph.
Thank you.
I think actually it's in Ohio, but I forgot what you said. So if you had explained what a deficiency one network was to a biologist who didn't want to do math, well, how would you tell them how to recognize a deficiency one network?
I would tell them about the bifunctional enzymes, right? Because that's a biological way to say something similar. But I mean, in principle, you would just do the procedure. But the reason it's called deficiency is because it has to do with what. Anyway, I don't want to get too far into the details of this. Let's talk about this towards the end if we have time. But let's just you can either take it at face value and calculate this, or you can think about it in terms of bifunctionality, and then that could be a non-mathematical way to reach this subject. Yeah. Okay, so let's start talking about the stochastic part of this. Let's do the toy model again, and throughout I'm going to keep coming back to the toy model, even though I'm really thinking of all these other systems as well, just for the sake of simplicity for the talk. Let's draw the Markov chain associated to the system. If you stick to the one stoichiometric class where a plus b is equal to n, let's say, these are all the possible states. You could have 0 and 0 of a, n of b, 1 and n minus 2, and so forth until n and 0. These are the intensities given by this reaction. For example, this corresponds to the reaction b goes to a, so because there's n of b, the rate of this is k2 times n, and so forth. So you go back and forth, but notice that this rate to go from here to here is k1 times n times 0, which is 0. So really, if you ever reach this state, you can never come back. It's an absorbing boundary. So you can start running this around. You can run this for a while using the Gillespie algorithm, but eventually, after who knows how long, you'll get here and you cannot come back. So if the first question is, does this system in the stochastic framework have some kind of robustness? The answer, unfortunately, is no, in the sense of steady state. At steady state, the system has value a, or n for a and 0 for b, and it's completely not robust. It very much depends on n. Okay? So that's unfortunate. You know, you might think that the system was somehow robust, but in this case, it really isn't at steady state. Let's see. So in a more or less recent paper published by David Aronson, Matthew Johnson, and myself, with the vast majority of the work done by David, it was proved that this is actually a very general property of these systems. It is not a fluke that the toy model has this property, but instead, if you take any such system, any system that satisfies these previous assumptions, and you throw one more assumption, then this funny boundary hitting the wall happens every time. In order to understand the theorem, let me just give you a small definition here. Two definitions. Okay, so you probably know this already, but a chemical reaction network is conservative if every species is involved in a mass conservation equation. A different way to say this is there is one big mass conservation equation involving every single species in the system. Okay? In particular, there cannot be, none of these proteins can be produced or destroyed. There's no degradation, there's no production. The proteins are just changing activity, phosphorylated, dephosphorylated, so forth. Another definition, if you give me concentrations for each of these variables, you know, concentration for X, for Xt, and so forth, we say that a node is turned off if at least one of the species in the system has concentration 0. Okay? And the intuition for it is, if there's one of these species with concentration 0, then this reaction cannot take place, because the rate is K3 times Xp times Y. Y0, say, the concentration, the reaction cannot take place. So the theorem now, here's the theorem. Suppose all the assumptions we had plus the system is conservative. Okay? Basically what this allows is that because it's conservative, the corresponding Markov process has only finitely many states, so you can look at it more carefully. It doesn't, you know, there's a lot of stuff that cannot happen. Then, here's the theorem. For every solution of the system, every non-terminal node eventually turns off and stays off. So every one of these blue nodes will turn off eventually. So eventually, at steady state, whatever it is, every one of these guys will have at least one variable with concentration 0. Now, let's see what this means more in practice. I'm gonna move on. Same system over here. We have two conservation laws, which is x dot equals xp plus x. These are all the different forms of x. Y dot is equal to yp plus y, all the different forms of y. There's 6 different forms of x, and 5 of them, this one, this one, this one, this one, this one, are by themselves in a node. So think about it. Because of this theorem, eventually at steady state, every one of these guys are going to be in concentration 0, because being off, you know, if this node is off, the only thing you can say is that xt has concentration 0 at steady state. So this is concentration 0 and so on and so forth. So therefore, all these 5 have concentration 0, and the only one that has not concentration 0 is xp. So at steady state, we conclude that xp is equal to x dot. All the x is in form xp. We can conclude that from the theorem. Second conclusion from the theorem. Because we know that xp is bigger than 0, and this is a blue node, so it's off at steady state, that means that y is equal to 0 at steady state, because you know that node has to be off. So y has concentration 0 at steady state. Similarly, this guy has concentration 0 at steady state because it's on its own. This guy has concentration 0 at steady state. So y dot is equal to yp at steady state. So you see it's actually quite a powerful result, because we can conclude in the system that at steady state, the only thing that can be happening is everything is every y molecule is in this form, and every x molecule is in this form. All right. Good. So in particular, it means that there's always some kind of collapse that makes everything look very, very different from the deterministic behavior. Okay, let's move on.
So,
Yes.
so is that what we're supposed to see on the right picture?
On the right picture, you have the following. Let's see. On the right picture, you have this is the distribution of yp according to a Gillespie simulation, and you do this after different amounts of time. So in the beginning, you know, you do this, I don't know, for 10,000 runs, and then if you do this for 100,000 runs, you see that the distribution starts looking funny. This distribution basically means that there is a non-zero chance of yp hitting the wall, hitting the boundary, and then it stays there.
Okay. So and eventually this will become a delta function.
Exactly. Eventually become a delta function. But in the beginning, you don't see that. In the beginning, you see something like this.
And how is it in the deterministic system? You're not going to go all the way to the delta function from the end?
You don't. You don't. In the deterministic system, you very much you just converge. In the deterministic system, you converge towards the state. So the deterministic and the stochastic behaviors are completely different.
Well, it is a delta function, but it's a delta function in a different point in some sense, in the deterministic case.
I see. Okay, fine, sure.
In the network that you're seeing, I cannot see how everything is not going to end up in XP and YP. I mean,
You mean deterministic?
yeah.
Let's see. Why it doesn't all end in XP, YP? What do you mean?
So everything, like whatever X you had, and the X total will go to XP, whatever Y total will go to YP.
Yes. That's what happens with the stochastic system.
And not the deterministic.
No, because the deterministic one, YP is absolutely robust. So the concentration of YP does not depend on Y tot.
Okay, okay.
But in the stochastic case, it is equal to Y tot. So it's very much not robust to Y tot.
A lot of the other species went to 0, right? Like,
Yep. All the other species go to 0. Okay, good. You guys are thinking about this. We're running out of time. Getting started.
I have plenty of time, don't worry.
Oh, okay. So, all right. Now, here's the good news. At least if you want to show some kind of robustness similar to the deterministic case, here's what happens. Let's go back to the toy model. If you take your computer, you run the Gillespie simulation for a while, let's say 20,000 runs or 100 units of time or something like that, you don't see this. You don't see this hitting the wall in the practice very much. Here, for example, I'm taking A tot equals 30, so I'm taking 30 molecules, and I'm running this for a while. And here's K1, here's K2. For the reference, K2 over K1 is 10. And here I'm drawing a Poisson distribution, and you can see that this distribution for a while, if you just run this on the computer for a while, the distribution looks a lot like a Poisson distribution. It does look robust. Not only is it Poisson, it's Poisson around the deterministic mean. So for all the world, it looks like it's robust. It's just, we know it's not because eventually it's going to hit the boundary. But in practice, it might take the age of the universe for it to hit the boundary, so in a sense, who cares, right? The biological system has only so much time to make a decision. If it's going to take the age of the universe to converge to the boundary, but you're going to make a decision in 5 minutes, then the transient behavior might be what matters in this case more. Of course, it depends on how much you have of the protein. If you only have 3 copies, maybe you will hit the boundary. So it depends on what regime you're interested in. But let's just say that in many cases, the transient behavior is the relevant behavior for making a decision. And in that case, if you're looking at transient behavior, there does seem to be robustness. And it does seem to very much correspond to the robustness of the deterministic system. Basically, you're hovering around the deterministic mean.
this requires that irreversible reaction rates are small compared to the others?
No. It's just that it's unlikely for you to get all the way, the boundary is hit when you get all the way to the boundary, and it's very, very, very unlikely to get to the boundary. And I haven't told you here why. In fact, to me, it's still kind of an open question. It's something that we'd be interested in to determine more about how long it takes until you hit the boundary. But in practice, it takes a very, very long time. Okay, so there you go. Simulations show consistently for this system, as well as for this more complicated system, that the system is robust transiently, but it does look robust until something terrible happens. So there you go. Here's many different simulations with many different values of X and Y top compared with the Poisson distribution, and our robust variable YP, all bar, is robust. So can we prove this mathematically? And that's what this next theorem is going to be about, is to prove, or to at least provide evidence of this mathematically. What I'm going to do is, here's back to the toy model. This is the Markov chain of the system, the Markov process. And I'm going to make a change of variables. This is K1 and K2, I'm going to define them. The K1 bar equal to K1 times n, and K2 bar equals to K2 times n. And I'm going to show you in a moment why. For now, when I write this in terms of the Ki bar instead of the Ki, I have to divide by n, and so I get these terms appearing. And notice these terms are n1, n minus 1 over n, and 2 minus 2 over n. When n is very big, all these guys become very, very close to 1. You see? And then what remains is something that looks a lot like, K2, 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 and then K1 times 1, K1 times 2, K1 times 3. it looks a lot like this Markov chain, like this Markov process. Now, what is this Markov process? This Markov process is none other than the Markov process associated to this chemical reaction, the simple birth-death process, which you probably know. And this system is well known to have a Poisson distribution. It converges to us a Poisson distribution quickly and just stays it. So it does seem like we're onto something, right? If you look at this network for large values of n, and for example, you look at a node here, and you look at the behavior around it, you look at the edges around this node, for very large n, this looks a whole lot like this network, okay? So presumably, because the edges are similar, and they become more and more similar for larger and larger values of n, presumably if you run the system for a finite time, it's going to look similar to running this system for a finite time. Yes?
I can see how that's true at this end of the chain. But when you get to the far end of the chain, the thing you
Yes.
want to avoid, then
Yeah.
n
why
minus
I
a
was-
big number over it doesn't look a lot
Yes,
like one number.
I was cheating a little bit, and I omitted that part. But you're absolutely right. So here, it doesn't look, this is nowhere near 1, right? But remember what happens. What happens is, when I'm making n very, very large, and I focus on a single node, even if it's this large, let's say it's 100, if this is the node 100, this looks nothing like 1. But when I make n equals to 1,000, then that right-hand side becomes further and further away. So it matters less and less. Okay, that's a good point.
But it becomes a matter from where you start.
Well, maybe, but the point is, as n goes to infinity, no matter where you start, formally this network looks a lot like this network at every node, locally around every node. So all I'm saying is there seems to be a formal similarity between this network and this network, but still there needs to be a proof. I'm not going to wave my hand and say therefore this converges to this.
I guess the point is that robust concentration is n independent, right?
That should be part of the argument. All right. So there you go. So this network becomes very, very similar to this network. But there's a whole bunch of problems here. First, is this a totally ad hoc procedure, or is this something that we can do for other examples and not just for this one example? Is this a one-off thing? And so we need a systematic way to go from this network to this, what I'm calling the reduced network. Systematic in the sense that if you have other examples, you can do the same. And what I'm going to do is, here's a systematic procedure. I'm going to formally set b equal to n. I'm going to say, let's pretend b is very, very large, and let's say b is equal to n. Just for the moment, just bear with me for a moment. I know it's a kind of crazy thing to do.
Sorry,
Yes.
just a quick question. Maybe I didn't understand, but when you take n to be very large, what does it mean in terms of the time the reaction takes place? Does it mean no reactions?
The stochastic or deterministic?
Let's say the stochastic.
Okay, if n is very large for the stochastic system, it means it would take very, very long for it to hit the boundary. But other than that, when you run it in the computer, A hovers around k2 over k1, and B hovers around a very, very large value, which is n minus
The
k2
question
over
is,
k1.
maybe my question is like this. If you have a biological process or some reaction that takes place or takes, I don't know, t minutes to finish, to get into this equilibrium, can you really take n to the infinity? Don't you have to like fit the n to the actual time of the process?
Yes, you definitely can.
So that
My
it will affect-
point, yeah, of course, you cannot make n go to infinity. You have a fixed n, let's say 100 or 200 or whatever. My point is that if we show that as n goes to infinity, the system becomes more like a Poisson process,
Right.
and n is 100, hopefully by that n is large enough that it will already look like a Poisson distribution. It's
For the time scales that you look at it.
for the time scale that you look at. If you run it for long enough, then it will go to the boundary. Okay, thanks for the question. Okay, so we need a systematic way to go from here to here for other chemical reactions. So here's one way to do it. Formally set b equal to n. I know it's a weird thing, I'm completely taking it out of my hat, but let's just say. And then because b is equal to n is not a species anymore, it's now more of a parameter, so we can take it out of the system. This reaction does not have b anymore, but it's just a goes to 0, and the rate got incorporated in n. So it's k1 times n, right? And this reaction is basically nothing because there's no species here anymore, goes to a at a rate equal to k2 times n, right? And now if you notice, this reaction is none other than this reaction using this hat notation or this bar notation that we have here. So there you go. You can go systematically from here to here by doing this procedure of freezing a variable. Now, the freezing of a variable you can do with any kind of system. You can choose any variable. It needs to be involved in a mass conservation law, but you can freeze it by setting it equal to the total amount of the protein. You can do this systematically. We're going to do this in a little bit, if we have time. But then the idea is you can systematically go from here to the reduced model. And okay, I guess I already said this. This system is well known to have a Poisson distribution. This neighbor becomes very similar to this neighbor when it is very large. Okay, fine. All right. So now here comes the general result that I'm claiming for this talk, which is the following. You have, once again, you have any chemical reaction neighbor with efficiency 1, the same assumptions as last time, conservative, positive equilibrium, non-terminal nodes, and now we're going to add that by freezing either one variable or multiple variables, we can reduce this system to a neighbor with efficiency 0. Okay? If you know about chemical reaction network theory, you know that efficiency 0 stochastic systems are very well behaved. So, by reducing it to a system with efficiency 0, we know a lot about the steady state of that, the quasi-stationary distribution of that system, and we can relate it back to the original network. The conclusion is that in that case, if we can do this, then the absolutely robust system for large T and for large total amount of concentration is going to look like a Poisson distribution. Now, more precisely, the statement will be, in this case, will be the following. If you look at the probability that yp is equal to some value, and you look at the limit, first of all, let's say we fix t, and we make the limit when x dot and y dot goes to infinity, this becomes very, very similar to a Poisson distribution. And as t goes to infinity, then it's not just approximately equal to, but it's actually equal to Poisson distribution. Okay, so that's the exact expression that I'm trying to prove.
I'm sorry, I'm
Yes.
slightly confused because in the limit we know it goes to a Dirac on
Yes.
the boundary. So
Very
how
good
can
question.
you look at the limit as t goes to infinity?
Very good question. Usually, when you study these systems and dynamical systems, usually what you do is you fix your parameters and you let t go to infinity. So it would be almost like flipping this around. You fix x dot, y dot, you let t go to infinity, and then you hit the boundary. So in a sense, the elegant approach here is you're just flipping the limits, and you go from studying the long-term stationary behavior to studying the transient behavior. All right. Okay, so another way to phrase this, let's suppose that we only have one mass conservation for the moment. Let's call it n. So the total amount of protein is n. When you fix n and you let t go to infinity, first you go through some scrambling around where there's no clear distribution. Then you go through something that looks a lot like a Poisson distribution, and then eventually you hit the extinction event, this hitting the boundary. That's what you see in simulations. Okay. What I'm proving in this statement is that for every t, let's just say, I'm going to put it like this. For every t, for every finite t, as you make n larger and larger and larger, this becomes more and more like a Poisson distribution. And as you make t larger and larger, then it becomes more and more like a Poisson distribution. So it becomes, this is approximately Poisson, and the further you head with t goes to infinity, the more it looks like a Poisson distribution. But really, for practical purposes, all you need to wait is for a small amount of time, let's say some reasonable amount of time, and basically what it takes for the reduced system to converge to a Poisson distribution. Remember, especially in a toy model, this reduced system, this birth-death process, converges towards a Poisson distribution. Whatever time it takes to reasonably converge towards a Poisson distribution, let's say 10 seconds or whatever, that's the amount of time you wait, and then as n goes to infinity, the system looks a lot like a Poisson distribution. Okay.
So
Yes.
so that means that is that for a simple system? Is it generally short or for a specific system?
No, this is in general.
Okay, so that means that on the non-dimensional time, independently of when you more or less start looking Poisson like around 10.
No, it's just an example. I mean, this basically is a cartoon. I mean, it's not around 10 because it depends on the time scale and everything.
Okay, but I mean there would be a time scale. But one thing that I think I can understand from this one is that the time scale that it takes to look like Poisson doesn't depend so much on n, but then how much time it takes to go to extinction depends critical on n. Is that correct?
Yes, very much. That's right.
Okay.
That's right. So this line is more or less vertical. There's some transitional time. that does not depend very much on n, but then the time that it stays Poisson very much depends on n. So if you have n equals 30 in the toy model, it will take very, very long time to converge towards the boundary, whereas if you have n equals 5, it might just take a small amount of time for you to converge towards the boundary. Okay, now the proof of this result, I'm going to give you a sketch of the proof, is very much what I just sketched for the toy model, just with a more complicated notation. That's why the toy model is so important, because it gives you all the right ideas. Basically, I take an arbitrary chemical reaction network with n plus 1, let's say, species. I'm going to assume I'm going to get rid of a n plus 1. This is the mass conservation law. And I can, let's just say the coefficient here is 1. Just I can divide by this coefficient otherwise. And I have this mass conservation law. So the first thing I'm going to do is I'm going to freeze the value of a n plus 1. I'm going to set it equal to n, just like I did before. So what new chemical reaction do I produce with that? Well, I can get rid of this species from the system because it's not a species anymore, and I can correct or adapt the values of the kinetics accordingly. So now this is n to the power of sjn plus 1, and an plus 1 disappears from the system. Okay, that's one thing that I can do. Separately, I'm going to write down. I'm not going to use the frozen system for the moment. I'm just going to do something very traditional and typical to do here, which is I'm going to eliminate this variable by writing it in terms of, I'm sorry, this is not t, this should be an n. I'm writing this system in terms of all the species, in terms of all the other species, and I'm going to basically just by virtue of doing that, I'm going to focus my attention on this one stoichiometric class, and this is the master equation of the original system after focusing my attention on this particular stoichiometric class. Okay, now I'm going to, once again, I'm not doing anything funny, I'm just changing the notation. I'm going to define kj bar like this, and once again, I'm just rephrasing the master equation so that it now looks like this. This is still the master equation of the original system. I haven't done anything funny here, but I'm rewritten it so that there's a whole bunch of n's here in these terms in the system. Now, on the other hand, when I look at the master equation of this frozen or reduced system, it looks like this. And you can see that there's a very close similarity between this system and this system. Namely, when n becomes very, very large, each of these terms goes to 1, and then formally, this vector field looks more and more like this vector field. So there you have this at least formal relation between this process and this process. As n goes to infinity, each of these terms becomes to 1, and this at least formally gets closer and closer to this. Okay, now if there were finitely many states in the Markov process, we conclude very trivially that because this vector field becomes more and more similar to this vector field, that the dynamics of these two systems are similar after finite time. In other words, if I run both systems with the same initial condition for a finite time t, then as n goes to infinity, the solution of this system becomes closer and closer to the solution of the second system. Again, if this was finitely many states, it would be trivial through right away, no problem. Because there's infinitely many states in the system, it's not so obvious. And later on, I'm going to tell you, a few slides if I have time, why this convergence of Markov processes, in a sense, holds. But let's just go with that for a moment. And so basically, because this system looks more and more like this system after as n goes to infinity, I'm going to assume that the solution of this becomes closer and closer to the solution of this for finite time. Remember, it only works for finite time. Infinite time, there's no comparison. Okay. All right. So you have this limit here. Now there's a little bit of analysis of the reduced model, which by assumption has efficiency 0. Because it has efficiency 0, it has lots of nice properties. Especially there's this, by now I would say, classic result by Anderson, Kashunen, and Kurtz, where it says that the stationary distribution of the system has a product form Poisson format. So here's the stationary distribution of this reduced system. And because the solution of the original system looks more and more like the solution of this system, as n goes to infinity, see, because y is equal to this limit, and this limit is this, then I can plug in x in here, and I get this equation, which is very much what I wanted to prove in the statement. namely that as n goes to infinity, and for large t, and especially when t goes to infinity, this is a product form Poisson distribution. In particular, if you look at a specific variable which has Poisson distribution, which is absolutely robust, then in the limit it has Poisson distribution. Okay, so that's basically the proof. Just compare these two systems and make this formal limit of Markov processes, and you're done. Yes.
And so you say it's Poisson, but it's also got a limit to how much of that species you can have. So is it more like a binomial or something, or?
Correct. It's not Poisson per se because there's finite. You're absolutely right. There's finitely many states. For example, the toy model only has n species. Even if you make n arbitrarily large, it still is finite. So the distribution is never exactly Poisson, but it becomes closer and closer to Poisson as n goes to infinity.
Okay.
All right. Now, I should say something a little bit more explicitly, which I didn't say before, which is as n becomes larger, I'm basically comparing this system with this reduced model, but I actually don't want the system to be dependent on n. I want the system to be fixed, and I want this to converge towards this. If my limiting process depends on n, it's kind of a moving target. So I want to set this system up so it doesn't depend on n. So what I do is I'm making k bars. If you remember, this system is has parameters k bars, right? This system has parameters k bars. In principle, we said that k bar is a function of n. But really what I'm going to do is I'm going to fix the values of the k bars, and I'm going to change the values of the k1 and the k2 accordingly, so that these guys are fixed. Okay. So once again, when I start varying n, I'm actually decreasing the value of k1 and k2 so that the k bars are constant. And formally what I do is, if I have experimental data, for example, these values of my estimated experimental values for the parameter rates, and some estimated value of the experimental value of the total amounts of protein, then I first define the ki's, then I define the ki bars, and then I define the ki's as a function of n, so that ki bar is constant. So this is a little bit tricky, that's why I didn't say it before, but basically I'm making this system fixed, and I'm changing the parameters here as n goes to infinity. This is some similarity with things that are very standard in stochastic theory, for instance. When you look at a binomial distribution, which you just brought up, binomial distribution with n subjects and probability p of having an event, as n goes to infinity and p goes to 0, this converges towards a Poisson distribution. But if you want this to converge towards a Poisson distribution as n becomes very large, you have to make p small. So you're changing your parameter, you're making your parameter smaller as you're making your n larger. Okay, so it's something similar. Basically, I'm making my parameters smaller as I'm making the number of individuals larger, so that the whole thing converges to something. And incidentally, this actually converges towards a Poisson distribution, so maybe there's some kind of relation there. But anyway, so it's, there you go. Okay, I'm running out of time. So this is an important slide in the sense that not only, if you run simulations, not only do you have a Poisson distribution, but you have a Poisson distribution around the deterministic mean. And that's important, right? Because that's robustness, right? That's a large part of the statement is that it's robust. I thought I had a proof of this, but when I was preparing for this talk a day or so ago, I realized I have a problem with this slide. So I need to think a little bit more about it. Let's just say for now, I'm making use of the absolute robustness of the original system and using it to transfer it to some form of robustness for the reduced system, and then I'm using that to prove robustness of the stochastic system. The Anderson Kurtz theorem is very clear about it. This is a Poisson distribution where the mean is lambda, where lambda is the mean, the steady state of the deterministic system, or the deterministic deficiency zero system. So if we understand well what the deterministic steady state is in the system, then we can understand why the system is robust. And that's what that proof boils down to. Okay, now let me give you a couple of examples about freezing, and I basically show you that you can do this procedure of freezing and and carrying out the theorem assumptions in more than just the toy model. First of all, let's do a generalized toy model. This is the same as a toy model that has n variables instead of 2. Also, the efficiency 1, it satisfies all the assumptions of the theorem. And what I'm going to do is I'm going to freeze the variable n plus 1. Okay, so I'm just going to go ahead and set this equal to n. So then this goes away. This reaction is now a1 goes to 0 with rate k1 times n, which I'm putting here. This reaction is now 0 goes to n with rate kn plus 1 times n, which is here. And the resulting system, sure enough, has the efficiency 0. It's quickly reversible, everything you want. We can analyze this and compare it with this, and this system has transiently approximately Poisson distribution, very much what the theorem says. Okay. Second example. Now we have 2 mass conservation equations instead of just 1. This is just to show you that I didn't cook this up. I'm taking this example straight from the Chenard paper. It's one of the examples in the paper. They call it the core model. It has 2 mass conservation equations. And in this case, I'm not going to freeze one variable. I'm going to freeze 2 variables. I'm going to freeze E and EIP. This one is set equal to E dot. This one is set equal to I dot. And the same thing happens. When I get rid of them and I freeze them in a very natural way, this system now has efficiency 0. I compare this system with this system, and the distribution is approximately Poisson. And finally, a third example, which is very similar to the system that I talked about at the beginning, has 2 mass conservation laws, also an MC and on-par model. In this case, once again, I was able to find 2 species to freeze so that the corresponding, the reduced system, after freezing them, has efficiency 0. I gotta say, you have to play around with it a little bit. It's not obvious. You have to play around, pick different variables to freeze. Eventually, you pick the right ones. With some luck, you freeze them. The resulting system has efficiency 0 and satisfies the assumptions of the theorem. And you're good. Obviously, there's a question, how often can you do this? With what examples can you do this? And it's something that we're thinking about working with David in the future, which is under what conditions you can guarantee that there are variables to freeze that will yield a efficiency 0 systems. Yes?
But could it be the case that you will have different choices of parameters
variables to freeze,
and that would give you different systems?
Yeah, it could happen.
But what would that actually mean? I mean, because if these systems, they have different Poisson distributions.
No, it should be the same. I mean, the system would be a different system, but the conclusion that you're drawing would be the same in the sense that the transient distribution of the absolutely robust variable is Poisson around the deterministic mean. See, the final statement that I make does not refer to the network. The final statement is the transient Poisson distribution is Poisson around the deterministic mean. I'm just using this as a means to get to the statement.
So the important thing is to be able to find at least one choice,
Exactly.
one combination of frozen variables.
Exactly. That's exactly right.
It doesn't need to be unique, but the intuition or the theorem is that even if it's not unique, the Poisson distribution would be unique.
Yeah, I think, for example, in this case, this is a pretty symmetric system. I guess you could, I'm not completely sure, but if you freeze A1 instead of A plus 1, maybe it would still work. I would have to check, but
Okay, yeah.
it's definitely not necessarily unique. Yeah. Or maybe even any of the other ones, right? I don't know. Okay. So you pick these 2, and you do it, and it doesn't work. Because this system doesn't have efficiency 0, it has efficiency 1, and it's not weakly reversible, which is another assumption of the. I'm sorry, it's not an assumption of the theorem, but if it's not weakly reversible, you're in even more trouble because the system does not have a Poisson distribution. Okay, but there's something to notice about this system, which is an interesting thing, is that x is now a useless variable that doesn't do absolutely anything. It is produced, it is destroyed. It is produced here as well, but it doesn't affect any of the variables in any way whatsoever. So, it basically is downstream of these variables. You can ignore it. By ignoring it, just by ignoring it, you get rid of it, and the resulting system now has the efficiency 0, and it satisfies the assumptions of the theorem. So even though you know, this is not, maybe not satisfying the assumptions of the theorem to the letter, in the sense that I'm not just freezing, but I'm freezing and ignoring a variable. I can still very much carry out the same argument. These variables have a Poisson distribution as quasi-stationary distribution, which is Poisson, and then I can compare this system with this system and do exactly the same thing.
X is in the terminal node, no? The second reaction on the terminal node.
Sorry?
X is in the terminal node of the second the middle reaction.
So this is the reduced frozen system. So at this point, it doesn't matter what the terminal nodes are.
Okay.
So hopefully there aren't actually any terminal nodes, because I want this to be strongly connected.
But the diagram shows the dot.
Yeah, sure, but that's what I'm saying. I'm eliminating x because it's a dummy variable.
Right.
When I eliminate it, this new system doesn't have that. It has efficiency 0 and everything works.
Are you talking about the same system, or are you talking about the system up?
No, the one up. Okay.
Oh, the one up is before you froze.
It's before the freezing.
Okay.
Right. Yeah.
Where the critical curve here seems to be xtyp, no, the bottom, down. Yeah, xtyp goes to empty set. Where did that come from? I don't see how getting rid of x gave you that.
Let's see. So xt. This is in the office. Let's see. So x goes to. You're right. There may be a typo in here. Yeah. So, actually, you can prove that. Yeah, I guess.
That's fine. I mean,
Yeah,
maybe there's a typo.
there may be a typo in here, but actually, you can prove that if the reduced system has efficiency 0, then it's weakly reversible for free. Then it has to be weakly reversible. So this weakly reversibility will come out just by checking that the efficiency is 0. And the efficiency of the system does not depend on this particular edge. It's the same whether you take it in or out.
Sorry, does he have xty? If you look at the third equation, it looks like you eliminated the xtyp complex when you conserved.
So, okay, so this x went away. So now yp, this yp and this yp are now the same node. So I'm putting them together.
Sorry.
And this goes back and forth to xtyp.
I'm saying you've gotten rid of xt plus yp goes to xtyp and already from the third blue, the original network, right? There is no, in your, even your first reduced model, there's no more xt plus yp anymore, right?
Oh.
Sorry, I guess that's what the yp. I forget what you eliminated. I mean, obviously
No,
you're using a
no,
conservation law.
No, but actually xtyp is a different variable from xt plus yp. They're different. This is different from xt plus yp.
Yeah, I understand that. So I'm saying you remove the xt plus yp using a conservation law, and I forget what variables are you removing, xt or?
Yeah, I don't know.
Okay.
I'm sorry. Okay, I did want to bring up how to carry out this limiting procedure. So I don't know, do we have still have time?
Maybe 5 minutes.
5 minutes? Okay, so let's do that. If you don't mind.
Sorry.
So,
I saw it.
oh, you saw it?
Yeah, if you go back. No. Okay, go on. Sorry.
Let's talk
Yeah,
about
yeah,
it.
it's okay. I just gotta say it.
Okay, so you have a series of Markov processes that formally converge towards a limit Markov process. Can we conclude that running this system for finite time makes the solution converges towards the solution of this limit system? That's what we would like to prove. And to study that, I'd like to bring up a very elegant technique that I learned from Mustafa Hamash and Brian Monsky called finite state projections. I don't know if you've probably heard of them. They're usually used numerically to do numerical simulations of master equations, but it turns out it's a very elegant theoretical technique as well. What it is you've probably seen it before, so I'm not gonna walk into much detail. You take pretty much an arbitrary discrete states Markov process. Any of these chemical reactions will do. You choose an arbitrary subset S. usually it's finite, but actually for this thing it doesn't even need to be finite. And everything that's outside of the set S, you collapse into a single state. And all the arrows that are coming out are still coming out, but now are coming out towards the single state G. And there's no arrows coming in. So all the arrows that were coming in, you just don't write them. So this new system obviously has an absorbing state G. So in the end, in steady state, it's going to converge towards everything is in G. But the point is, if you run it for just a finite amount of time, you may get solutions that are similar to the solutions of the original system. Which, if you think about it, is a very similar situation from what we have in our system. There's two lemmas. I'm going to call this system the variable with the variable y, and I'm going to call this with the variable z. First lemma is that if you run both systems with the same initial conditions, let's say as initial conditions supported in this set, then the zi's are always less or equal than the corresponding yi. And I don't have time to show you the proof, but the proof is actually very short. It's just a monotonicity property. Lemma 2 is that this expression, which you can think about as the error between the y's and the z's, you see is the sum over all I and s, is the difference between them. And then you're adding all these guys, which we don't even have there, but you're just adding them. This is basically some kind of error between these two. And this error is none other than this variable, the variable z evaluated at time t, at this point g. So what happens? If you run this for a while, and this is very, very small, you know that the error is small. That's why it's numerically so important. And the proof is almost trivial. What you do is, you first use the lemma 1 to show this, you can get rid of the absolute values because this is bigger or equal to this, and then you add all the zi's, you add them over there. Over here you get 1, and over here you get 1. That's the proof.
Can I ask something about lemma 1? Sorry, I don't want to slow you down, but okay, but these are stochastic processes, so what do you mean that zi of t is less than yi of t? In what sense? In probability?
No, these are actually scalars because I'm looking at
Realization.
No, well, I'm actually thinking about it from an ODE perspective. It's a finite. This is a finite ODE if you just focus it on this.
Okay, so but we're talking about ODEs, not Markov processes now. Sorry, I'm confused.
So this is the solution of a system of differential equations, and every one of these variables for every I in the set,
okay,
this is a function of time, right? It's the probability that you're going to be at that state at time t.
Okay, it's just because that you say can be carried out for continuous time Markov processes, so in there. Anyway, so but z y prime equals l y and z prime equals k z, these are ODEs that you're talking about, basically.
Yes, this is the solution. Every one of these guys
the
is
master
a
equation
solution.
for the continuous time Markov chain.
The master equation.
Okay.
So this is really less or equal in the sense of just real values, and so are these.
So these are kind of probabilities in some sense.
Yeah, this is the probability that you're going to be at state I at time t.
Okay, perfect. Okay, thank you.
All right. So so lemma 1 again. Lemma 1 is less. This is less or equal than this. These guys are less or equal than these guys. And lemma 2 is that the error is small. The difference between these two guys is small. Now I'm going to systematically use that to prove the limit of the Markov process. The first thing I do, and this I'm going to do with the toy model here, but the proof is very, very similar in the more general case. If you remember, this is the reduced birth-death process, right? The birth-death process with Poisson distribution. And I'm going to make a finite state projection just with the first m states. Okay, this is just the usual. These intensities are the same, and instead of having all these Taylor reactions, I just have one single node, and then the intensity going there. That's it. Okay. So the first thing I prove is that for every one of these nodes, the limit as m goes to infinity of this is yi. This is the ci's, this is the yi's. Okay? And this maybe makes sense intuitively, but here's a proof. The difference between these two guys, by the lemma 1, I'm just going to refer to them as lemma 1, I can drop the absolute values because this is bigger or equal than this. This is less or equal than the sum over all of these guys. Now by lemma 2, this is less or equal than this. This by definition is the integral. So this node only has an input from this guy. So this can be written as the integral from 0 to t of this. Now once again lemma 1, I'm replacing c by y because y is bigger than z. And because the y looks a lot like a Poisson distribution, I can write this less or equal than a constant times Poisson distribution at that point. And because this becomes a constant, I can write this as t times the constant. In this guy goes to 0 as m goes to infinity. So there you go. So as m becomes very large, every one of these nodes, the solution of it, becomes very, very similar to the original reduced model, to the birth-death process. Now the next step is I'm going to do the same thing. It's a little bit more complicated with the original system. The original system, if you remember, looks like this. Okay, it goes all the way to n0, but I'm going to pick the m first nodes, and I'm going to just go ahead and do a finite state projection right up until that point. And I'm going to call these guys x's, and I'm going to call these guys w's. And what I'm going to show is that not only do the x's and the w's become very similar to each other, basically everything becomes very similar to each other. The statement that I care about is that the x's become very similar to the y's. That's really what I want to prove, right? That at finite time t in any state I, this limit is equal to this. And how do I prove it? Well, first, the first thing I note is that if you look at the w's and the z's, if you fix m and you let n go to infinity, these nodes become very, very similar to these nodes, to these edges. And so, because it's finite, this goes towards this. The w's converge towards the z's. Right? So this, as n goes to infinity, this goes to 1, all these go to 1. Now, Carter, we don't have the problem you were saying because we're cutting it off at m. So we're only looking at the first m. So when we make n really large, these all go to 1, and these solutions go towards this.
Does it mean you take a smaller and smaller portion of your process? I mean, G has more and more nodes, right?
You have to carefully make m and n go to infinity in a very careful way. So you're right, but it still works. But you're right. You do need to be careful.
Everything becomes like a very, very small process inside.
Yeah, I think that's part of the argument. Yeah.
It's indistinguishable.
Yeah. So so then the w's and the z's are very similar. But remember, we already said the y's and the z's are very similar. These are the y's, these are the z's. So I'm going to wave my hand a little bit just to spare you the more technical inequalities, and just assume that the y's are similar to the w's as much as we want, as much as we need. And let's make m sufficiently large. Okay, so this inequality is always true for any two variables. But then, because we know that the y's and the w's are very small, are very similar, I can bound this arbitrarily. I can make this as small as I want. And if you remember, the y's are a Poisson distribution. They become very similar to a Poisson distribution. So if I make m sufficiently large, remember this set S becomes bigger and bigger when I make m larger, I can make this arbitrarily close to 1. So this becomes arbitrarily close to 1, this becomes arbitrarily small, so this is bigger or equal than 1 minus epsilon. Okay, and now the difference between the x's and the y's, and again, I'm waving my hands a tiny bit because I'm going to assume that the y's and w's are similar. This is roughly equal to this, but now comes again the dilemmas from the finite state projection. This is equal to this because by the finite state projection, this is bigger or equal than this. Remember, finite state projection. Now this is less or equal than this. Once again, by using the fact that the w's are less or equal than the x's. This is the reason that I can say that this is less or equal than this. And these guys are less or equal than 1, and these guys are almost 1. They're bigger or equal than 1 minus epsilon. So this is less or equal than 1 minus 1 minus epsilon, which is epsilon. So by carefully bounding everything from below, using this finite state projection lemmas, I can actually show that the x's converges towards the y's. Anyways, bit fast, but you know, I'm happy to answer questions if you have any questions about this later or even now. And that's it. So, okay. So the conclusion is absolute robustness is a property that you can test by just looking at the structure, the topology of the system, without regards to the parameters, which is very valuable in biology. If you look at the stochastic system, unfortunately, after sufficiently long time, there's an extinction event that makes everything collapse and look very, very different from the deterministic system. But, however, the good news is if you just wait for a while, you don't wait until there's an extinction, but instead make the total amount of proteins larger and larger, then the system becomes closer and closer to a Poisson distribution, which essentially reconstitutes the deterministic framework. And there's many different ways that you can expand on this. In fact, we use this idea of the efficiency being zero only in a relatively weak way, that the distribution is Poisson of this reduced system. But there may be a lot of other possibilities. And part of what we did is we used finite state projections to show that a sequence of Markov processes converges in dynamics to this limiting Markov process. And we came up with a bunch of examples to the Shinaram in Feinberg paper, and to show you that I'm not cooking the models, I'm using the exact same networks that were shown in this paper. In future work is, I told you, I just inserted this yesterday because I do need some more to show that the approximately Poisson distribution is centered around the deterministic mean of the system. I would like to use this limiting procedure in other cases. If you notice, not only do you have Poisson distribution for the robust variable, you have Poisson distribution for everything. You have that the system becomes closer and closer to something that is product form Poisson. There's going to be a whole bunch of applications of that statement. For example, you can show that we heard talk by Ramon Grima not too long ago, where he said that certain nonlinear systems have surprisingly good behavior when you do things like linear noise approximation or fluctuation dissipation. So I believe that when the deficiency of the system is small, using techniques such as the one that I just did, you can show that there's unreasonably good approximation of these noise techniques. Like if you do linear noise, you may get a very, very surprisingly good approximation because of these using a proof along the same lines. And then I would like to continue work with David Anderson. We would like to do things like sufficient conditions for when you can actually find one of these deficiency zero networks, and to study the stability of the absolutely robust steady state, which is, by the way, there's no statement anywhere showing that the system has to be stable at that point. It's just something that you show there is a steady state, but there's no stability statement. So that would be nice to be able to use stochastic ideas to prove that. And eventually, I'll also be interested in doing and studying the time that it takes to reach extinction in these systems. Sorry for running over. I would like to thank my colleagues, Balayoshi, who came to visit recently and got me inspired with this frozen thing. He had something related to this freezing a variable in a different paper, and I started thinking about it, how it relates to this case as well. Jeremy Gulavardina, David Anderson, Matthew Johnston, co-authors in this other paper, Sam Isaacson in the Newton Institute, and Jay Newby and Roman for conversations. Questions?
I suggest we might ask one or two questions, then we take it over to over coffee, basically.
So the pseudobiologist in me left when you started doing the proof. So the question is, where did you use deficiency 1 in your proof?
I actually used that the reduced model has efficiency 0.
Right. But is that a separate state, or is it like you only get that possibly if the original thing was deficiency 1?
No, in fact, you can also do this with efficiency 2 systems.
Okay.
Come to think of it, I could probably drop that assumption entirely, because when I assume that the reduced system has efficiency 0, that's very much incorporating the information I need. So yeah, you're right. Good point. Yes?
In reality, extinction would be a bad thing. So you would have thought that there are some other reactions that are introducing these proteins or not. So I guess my question is, I mean, it's sort of related to what we've been talking about, that once you introduce other reactions into that network that are going to stop that extinction, you may not have absolute robustness, but you might have something which is epsilon close to robustness.
That's a great question. If you have even a small amount of protein production, then there's no sticky boundary anymore. So you could think about correcting for that in that sense. In fact, we know that there is protein production, even at a very small level or a different slow time scale. We know that that's happening. So that's another way to argue that this limit maybe is not this mathematical statement that you converge to as a boundary should be taken with a grain of salt, and it's more the transient distribution that you should look at. That's another argument to say that, I guess.
And so you mentioned several times that you were interested in the time, to the threshold, to your boundary.
Yes.
This is completely different type of mathematics or analysis, because usually you have to calculate path in this 2 or whatever dimensional graph of your Markov chain, continuous Markov. Have you started looking at this or not?
Not in any rigorous way, and I could see that it could be difficult. There's some techniques that I'm thinking about using. There's some standard techniques, but I don't know to what extent they could be useful here, because it's a very large family of networks, right? It's not clear how to attack it.
Sure, it depends on the particular type of network, especially n is not large, and if you want to calculate things, usually you have to consider path, and this is completely different type of approaches that we can present.
If you have ideas about how one can do that, I'd be happy to.
Yeah, we publish several papers on this.
Oh, really?
You have graphs, and then sometimes you can have, not exactly in the same framework that you have, but you can have a conditional probability that you arrive in one state versus another.
Yeah.
So you have to look at all the paths that finish in one.
And then when you put them all together, you can get an idea of the overall.
Yeah, and you can even calculate the conditional mean first passage time, condition that you arrive in one final state compared to the other. It's a completely different type of mathematical approach.
Okay. Thanks.
I suggest we take it over for coffee. Thank you.